Okay, so our final talk of the session is going to be given by Jan van Brügge from Heriot-Watt, and he's going to tell us about Barendregt, about rule induction for syntax.
Yeah. Hello, I'm Jan, and this is joint work with James McKinna, Andrei Popescu, and Dmitriy Traytel. And I present Barendregt Convenes with Knaster and Tarski, strong rule induction for syntax with bindings. So what's the key problem here? So assume we have some relation defined over syntax that contains binders. In this case, beta reduction for lambda calculus. And we want to prove some property about the system. In this case, we want to prove, okay, if I can step from m to n, I want to also know that I can step from m where I do a substitution to n where I do the same substitution. Fairly simple property. Ideally, I want to prove this property by induction on the relation itself. I do not want to prove this by induction on one of the arguments. That will make the proof much harder. However, if I look at the xi case, I will end up in my goal with a substitution over a lambda. So ideally, to progress this proof, I would need to move the lambda, the substitution into the lambda. However, I can only do so if I know that the variables are not the same. But our assumption doesn't give us this extra information. So at this point, I would be stuck in the proof, and I would need to do a lot of manual busy work to get this proof to work. So what we need here is the variable convention that says, well, the binders we introduce in that case are different from whatever I care about, or the free variables in this case. So how is the status quo here? So in pen and paper proofs, this is rather easy. We just say, yeah, well, we assume variables are different from the free ones. Then it depends a bit on the representations in theorem provers. For de Bruijn, we do not need to strengthen anything. However, in the proofs, we then get shifting bureaucracy with the substitution. There are techniques to avoid that, but that's the main issue with naked de Bruijn. Higher order abstract syntax, if it works great. However, it's hard to model binders that are more complex than what the host language provides. And also for some proofs, having a deep embedding of a language is better. So in nominal, or in this case Isabel, to be precise, there is prior work on this in the form of nominal too. However, this has some annoying limitation as the authors themselves state. So what are these limitations? So if I have the beta rule, to be able to derive an induction theorem that has the variable convention built in, for nominal, we need to attach extra side conditions, extra freshness side conditions to these rules. And in this case, the side condition is not like anywhere presented in a textbook. It is not needed because substitution doesn't care if the result has the variable again. It's just there so we can derive this strong induction theorem. So that's not nice. This gets even worse in more complicated examples. This is from our paper. This is the process calculus, and everything that's colored gray is extra side conditions that should not be there. And that's the status quo for this. There's another problem. They employ like syntactic criteria on the rules that define our relation. And this is syntactic criteria, which mean it rules out very useful things like quantifiers and higher order relations. So our contributions in this work are, we provide a generic semantic criteria that is detached from the specific syntactic format of the whatever rules we define. And we have an implementation in Isabel Hall that takes an inductive predicate and a proof of this criteria and gives back a strengthened induction theorem, which can then be used to do proofs like mentioned in the beginning. And we even have a heuristic that is implemented, which can in many cases prove this criteria fully automatic. And to validate all of these, we have provided several case studies, which I will talk about later. So going one step back, how can we actually bring this rather textual definition of a relation into a theorem prover? And what we mean when we talk about these rules is like that beta reduction is the smallest relation that is closed under these introduction rules. And if we say, well, the rule is smallest and closed, this might scream a fixed point to you, to the avid reader. And that's exactly what we do. We represent inductive relations as fixed points of some operator. So how do we find this operator? Well, we want to fix point which will be a relation. So the first argument will be the relation we define in the fixed point. And in this case, our relation has two arguments, the left and the right-hand side of our stepping relation. Focusing just on beta itself, in this case, we don't have any assumptions. We just need to constrain the left and right-hand side to have the right shape compared to what we wanted. We can do a similar thing for the psi case, just that we have now an inductive step. So we use that first argument that represents the relation itself to mean that. And of course, the other rules work exactly the same. So now we can define beta reduction in a theorem prover. And because this function in there is monotonic, we know, thanks to Knaster and Tarski, that this fixed point actually does exist. So this is nothing new. This is standard. It's already implemented in Isabelle for many years. So how can we bring binders into that mix? We need first to know in every case what are the variables that this case opens up. For this beta reduction, there's only two cases, this beta, which mentions a naked binder, and the psi case. So we record this in this extra argument like this. And it's pretty clear that this operator is still monotonic, so there is, again, a fixed point of this thing. And we can define this called beta g, which just adds an existential for this thing. So this is not yet an improvement over the normal beta reduction, but we will improve this later on. But for this simplified version, it's very trivial to prove that this forms the same relation as the original beta reduction. So before we can actually bring in the strong induction, we need to have some extra criteria on our relation. One, the arguments need to form nominal sets. So a nominal set are two sets, V and A, with a permutation operation, which maps from V, which will be variables, or everything you use to represent variables, to a bijection of that to a function on the set A, and a support operator which extracts a set of these variables from a value of the set A. In typical nominal logic, this set V is implicit the set of atoms that is axiomatized as part of the nominal logic axioms. We work in higher order logic without any extra axioms, so we leave this to be decided by the user. In particular, we can say, well, we use strings for our variable names, and our A is the set of, or the type of lambda terms. And then permutation becomes substitution, and the support are the free variables of the term. We also need two extra conditions, equivariance and refreshability. The relation is exactly then equivariant if we permute with a bijection, in this case pi, all the arguments to the operator, the relation still holds. So this will capture us that we do not depend on the particular choice of names. This will rule out predicates that, for example, strip binders off and store them in a list, something like this, because they would not be equivariant. The other condition is refreshability, and this distills this what we mean by by freshness. So if we have our rules for every choice of rules, we need to be able to find a set of binders that is different from all of the free variables that appear in the rule. And that's exactly what captures the variable convention by meaning the bound variables are different from the free ones. Note that this is the generalization of what nominal 2 provides. So nominal requires you to have that be inherent. So the B that you use in the rules needs to already be fresh. And that's the main source why we need all of these extra side conditions, because we make sure that the free variables do not clash with any of the binders. So if we have these conditions for our relation, we can define a new thing called beta fresh, where we add these extra assumptions inside the fixed point. And with these conditions, we can prove that this is the same as the beta g we mentioned earlier, and as I said, the proof that beta g is the same as beta is trivial. So at that point, we can use the induction theorem that stems from this fixed point of beta fresh. We can use it to build to provide an induction theorem for beta that has the freshness built in. So how does it look for the user in Isabelle itself? So this is a normal Isabelle inductive definition, like many people probably have used already. And this is the new part. We can use the binder inductive command to strengthen this step relation. And in this case, as I said, we have implemented a heuristic. We do not need to prove either the nominal set structure nor the equivariance or refreshability. It's all automatic in this case. And then the proof I presented on the first slide is easy with this binder induction method we have implemented that lets you avoid the variables of certain parts in your rule. So what are the key advantages of this approach? So this is completely independent on how we state our rules. There's no syntactic limitation on what we can write and what we cannot write. They are all fixed points in the end. And we do not need to have these extra side conditions that are just there to satisfy the system. You get the freshness as an output of this process, not as an input. And this also, of course, has the bonus that you do not need to prove that the version with side conditions is the same as the version with outside conditions, because this proof, as seen earlier, we can do automatically. So in the paper, we have a bit more. We have generalizations for using inductive information for refreshability. That's also why there's two separate commands for this. So you can do normal inductive proofs in between and then use these proofs to strengthen. We have support for infinite types for this by generalizing what a nominal set is, and also non-equivariant relations. And we generalize this based on the case studies. So the first one is, of course, the beta reduction I talked about the whole time. Then transitivity of subtyping in system F sub. This is interesting because it exactly requires this inductive information. Reduction in the process calculus, which is interesting because of the scope extension axiom, which has a weird binding structure within the relation, in the reduction relation. And Damiano Mazza's infinitary lambda calculus, which forces us to reason about infinite syntax and non-equivariant syntax. Of course, we stand on the shoulders of giants, so very important for this work are like ideas of nominal logic by Pitts and Gabay, and also work specifically in Isabelle from Urban, Karliczek, Berghofer, and Norrish. And more related was, of course, in the paper. So to summarize, inductive definition are least fixed points. Refreshable and equivariant relations we can strengthen to have nice induction theorems. We can automate most cases fully and many cases mostly. And this is general enough to work with infinite syntax. Thank you.
Okay, so we have plenty of time for questions. So
Is this on?
you might be muted.
Okay. Hello? Okay, cool. Thanks for the talk. So you mentioned in the beginning kind of one reason you didn't want to look too much at higher order abstract syntax was that it doesn't generalize well beyond the kind of host notion of substitution. Do you have any maybe progress on like case studies or some inkling as to how this worked for a substructural type system or something like that?
Sorry, I didn't understand. What substitution?
You mentioned in the beginning that higher order abstract syntax wasn't a good approach for you because it was hard to generalize beyond the like host notion of variable and substitution. So in this setting, I guess I'm curious what that looks like. If you have any like case studies or at least like thoughts about extending to something like.
Yeah, so we don't we haven't looked directly at higher order abstract symbol because we work in Isabelle mostly, and we wanted to bring this to Isabelle. And Isabelle has a very limited, like it has only single binders.
Oh, sure. So I'm not saying you need to justify that choice. I'm just asking, like, does it?
So no, we hadn't looked at
okay.
anything from higher order abstract syntax because the context is just not
But
there.
I mean, like, do you have any? Sorry, do you have any thoughts about like a linear type system or something like that in this setting? Never mind. It's fine. I'll ask you offline. Yeah.
What system?
This.
Yeah,
system
this.
that, yeah.
So all the case studies are done with the automation and the system we developed. So because your linear type system would be a deep embedding anyways, it depends on what rules you define. So yeah, it would work with anything.
Okay, thank you.
Okay, do we have any other questions? Ah, there's some over there.
So very nice talk. Thank you very much. You were mentioning rules that were difficult. I'm using the open rule in the 𝜆-calculus, where you have a binder on the left-hand side which disappears on the right-hand side. So it's bound on one side but free on the other. So in nominal logic, that actually means that you must place an explicit permutation in your rule in order to make this work and keep it equivariant. Is this one of the rules that would still be a problem for you?
No, so actually for the 𝜆-calculus, the heuristic is strong enough to work with that. So we do not need, the user do not need to put any explicit permutation or anything on there. The whole permutation structure, the normal set structure is fully implicit.
Including the open rule?
Including for, yes, we have both late and early transition fully formalized in Isabelle, in one of the case studies.
Okay, any other questions? Be on this side of the room. Okay, I have one question too.
Yeah.
So you did this all in Isabelle. Have you thought what it would look like if you tried to do it in Lean or Coq?
So the main problem there is that we work with names. And representing names without quotients is annoying. So that's why we have not looked more. It probably, if you use something like higher inductive types in Agda or something like that, this would be adaptable. But without quotients, I don't think this would be very usable for the use, because we do make use of equality for these alpha equivalent types.
Okay, we have one more question over there.
So I wanted to, so this is like, I was paying attention to some of these things where we were just dealing with a more fundamental problem of binding in the first place when I was a grad student a couple decades ago, and then I was away. And so this is sort of extending on the maybe a clarification of the standing of shoulders of giants. Where does this, can you say a little bit more about what this does, that the techniques that were developed in Coq don't do? Where a little bit more about the diff between what this enables and what, like, you know, the locally nameless and cofinite quantification. What the techniques that are used in other systems are.
So I'm not familiar with cofinite stuff, but for the Brown or locally nameless, it is the main difference is that you do not have to do any reasoning. This is more work to set up. Mm-hmm. But once you have a setup, you just have an induction theorem, and you don't the freshness and does not leak into your proofs. With different versions of the Brown, you will have some sort of shifting lemmas or in your actual proofs about the system, because the Brown is fundamentally leaky, and also locally nameless has the same problems. So that's the main. Like, this is more work to set up, but we can automate that. And afterwards, it gets completely out of the way, and you just use binder induction, and you just get extra assumptions for freshness.
Okay, so let's all thank the speaker one more time.